Welcome to AI Paper Slop. Today's paper is Gamma World. It's titled Generative Multi-Agent World Modeling Beyond Two Players, published in 2026 by researchers at NVIDIA, Tsinghua University, the University of Toronto, and the Vector Institute.
Quite the lineup.
Right. Yeah, it's a heavyweight paper. And look, if you're an ML engineer or an AI researcher working on world models, I'm just going to give you the 60-second summary of why this paper is a massive breakthrough right up front.
Let's hear it.
So currently, multi-agent video generation is totally bottlenecked by two structural flaws. You've got computationally explosive dense attention, and you have these rigid learned player ID slots.
Right, which completely ruins scaling.
Exactly.
Yeah.
And Gamma World solves this multi-agent bottleneck completely. It introduces this thing called Simplex Rotary Agent Encoding, which is, it creates a 4D permutation symmetric geometry for agent IDs.
It's beautiful math, honestly.
It really is. And then it utilizes Sparse Hub Attention, which takes that cross-agent attention from a quadratic compute cost and just, forces it down to a linear one.
Yep.
They pass this incredibly efficient architecture through a really rigorous 3-stage distillation pipeline. And the result, they achieve 24 frames per second autoregressive streaming with independent KV caching.
Which is wild.
I know. And the model is so robust, it generalizes zero shot. Like, they trained it on just 2 players, but it can render coherent, interactive 4-player worlds at inference.
To put this into immediate perspective, for, anyone listening who's building embodied AI or, robotic simulations or even next-gen interactive game engines, this is the blueprint.
Yeah.
It is the architectural blueprint you've been waiting for. We are finally moving past the era of solitary single viewpoint environments.
Which we've been stuck in for a while.
Too long.
Yeah.
Gamma World demonstrates the exact mechanisms you need to scale to populated, highly interactive shared worlds. And it does it without, completely frying your compute cluster in the process.
Right, which is the dream.
Yeah.
The ultimate goal here is that 24 frames per second multi-agent streaming. But, to really appreciate why Gamma World's architecture is such a huge structural leap, I think we first need to examine why existing models just fundamentally break down.
Break down the second you try to add a third or fourth player.
Yeah, exactly. Okay, well, let's unpack this. Why does the current paradigm fail so hard?
Well, if you look at the current landscape of leading video world model systems like Sora or Cosmos, they are, at their absolute core, single-agent simulators.
Right.
They essentially roll out future observations conditioned on one single action stream or, one user input. There have been concurrent works, specifically a model called Solaris, which actually attempted to build a multi-agent simulator inside Minecraft.
But they hit a wall.
A massive wall. The problem is that Solaris, and honestly similar concurrent models, they relied on 2 specific design choices that structurally limit their ability to scale.
And those...
The first one is dense joint attention across all agent tokens. And the second is using learned per-player ID embeddings just to tell the agents apart.
Okay, let's focus on that dense joint attention first, because if you're a practitioner managing a compute budget right now, this is the pain point you actually care about.
Oh, absolutely.
A lot of people visualize dense attention like a crowded dinner party, but for our audience, I think a better analogy is network topology in multiplayer gaming.
That's a great way to frame it.
Right, so think of dense joint attention like an old-school peer-to-peer network. If 2 players are in a game, they send data directly to each other, one connection.
Easy enough.
But if you have 8 players, every single player has to simultaneously send and receive data from the other 7 players at every single tick. That is a full mesh network.
Which is chaos. Mathematically, the complexity is big O of p squared. It grows quadratically with every new player you add to the sequence.
You simply cannot run a full mesh attention grid across massive sequence lengths in real time.
You really can't. The latency spikes just become insurmountable. And the second flaw, the fixed slot IDs. That creates a completely different kind of bottleneck, a theoretical one.
Yeah, explain that one, because I think it's less obvious.
So when you train a model with a literal, player 1 embedding and a separate player 2 embedding, you're locking the model into a fixed roster.
Right.
You're structurally tying the model's hands because that fixed roster violates the core principle of how shared physical worlds actually function.
Because agents in a shared physical or, virtual space are intrinsically exchangeable.
Exactly the point. Think about 2 identical robotic arms on a factory assembly line. Or, say, 2 players in a digital game who have the exact same capabilities and avatars.
Yeah.
If they physically swap positions, the underlying physics, the lighting, the rules of the world, None of that changes at all.
The world doesn't care who is player one.
Right. The neural network shouldn't treat them differently just because one happens to be plugged into the arbitrary player one slot and the other into player two.
That makes total sense.
It's the foundational concept of permutation symmetry. A learned per-slot ID embedding completely destroys that symmetry. It essentially forces the network to learn entirely separate interaction dynamics for player one versus player two, rather than just learning the generalized laws of the environment.
Right, it's memorizing roles instead of learning physics.
Exactly. The authors of Gamma World argue that we need an architecture that is permutation symmetric from the ground up.
Which, I mean, that creates a fascinating paradox. If learned slot IDs destroy permutation symmetry and limit your ability to zero-shot scale to more players, how do you encode agent identity?
Yeah, it's a tricky problem.
Like, how does the model actually know who is who and whose actions belong to which visual stream without breaking the underlying math?
Gamma World's answer is to rethink how the model understands position itself.
And this is the first major contribution of the paper, right? The Simplex Rotary Agent Encoding.
Yep. For the researchers listening, you're probably already intimately familiar with 3D ROPE, or rotary position embedding, which, factors your attention mechanisms across temporal, height, and width axes.
Super standard stuff now.
Right. Gamma World extends this standard 3D ROPE into a 4D ROPE by explicitly adding an agent axis.
But the critical detail is how they handle that axis, because they don't just assign scalar indices to the agents, like labeling them 1, 2, 3, and 4 on a flat number line.
No, because if you put them on a 1D number line, player 1 and player 4 are mathematically further apart in the latent space than player 1 and player 2.
Which implies some sort of spatial bias or hierarchical relationship that, just shouldn't exist in a shared environment.
It shatters the permutation symmetry immediately. So to fix this, the researchers mapped the agents to the vertices of a regular simplex in the rotary angle space.
Here is where it gets really interesting. To give you a crisp geometric mental model for this, if you have 3 players in your simulation, imagine an equilateral triangle. If you have 4 players, imagine a perfect 3D tetrahedron. By placing the agent IDs at the vertices of a simplex, every single agent is the exact same mathematical distance from every other agent.
It's incredibly elegant.
And the paper actually proves this formally. They show that the squared distance between any 2 distinct agents is exactly 2v divided by v minus 1, where v is the total pool size of your simplex.
Right. Nobody is the main character. They are perfectly equidistant, perfectly exchangeable.
It's brilliant.
And the true beauty of this simplex ROPE for anyone actually writing the code is that it is entirely parameter-free.
Oh, wow, really?
Yeah. You do not have to learn these embeddings during the training loop. You simply define a fixed pool of simplex vertices in advance. When you run the model at inference time, you randomly sample an unused vertex from that predefined pool and assign it to an active agent. The modulation operates entirely in the low-frequency temporal band of the rotary dimensions, meaning it doesn't interfere with the high-frequency spatial details the model is, trying to render.
That parameter-free nature has to be the secret sauce for scaling. Because it is purely geometric, Gamma World can train exclusively on 2-player data, learn the physics of the world, and then at inference time, you can just activate 2 more unused vertices from that simplex pool.
Exactly.
Suddenly, you can perfectly separate the identities of 4 players without any additional training or fine-tuning.
It's a highly elegant mathematical solution to the identity problem. But, as you alluded to earlier, establishing identity is really only half the battle.
Right.
You have a beautifully symmetric way to tell the agents apart, but they still have to interact. They still need to visually process what the other agents are doing to maintain a consistent shared reality.
And we are still trying to avoid the full mesh peer-to-peer network scenario. If they are all mathematically equal, how do they, look at the same block of dirt being mined in Minecraft without immediately causing that quadratic compute bottleneck?
This brings us to their second major architectural breakthrough.
Yeah.
Sparse Hub Attention.
Okay, lay it on us.
Instead of that dense all-to-all attention grid, where every single token from player 1 attends to every token from player 2, 3, and 4, Gamma World introduces a small, centralized set of learnable hub tokens.
Okay.
Inside each causal block of the transformer, an agent's tokens only attend to 2 specific things: their own past visual stream and these global hub tokens.
Okay, wait, I have to push back on this, or at least play devil's advocate for a moment.
Go for it.
Because this sounds almost too simple to work in a high-fidelity rendering environment. If you're simulating a complex, multi-agent Minecraft world, players are building structures, they're mining, navigating around each other. Doesn't funneling the entire shared reality of the simulation through a handful of centralized hub tokens create an extreme information bottleneck?
It's a very fair question.
Like, how many hub tokens are actually required to hold the state of a massive multiplayer world?
It's arguably the most critical question regarding this architecture, and the researchers dedicated extensive ablation studies just to figure it out.
And what did they find?
They swept the hub size, which they denote as K, testing 1, 8, 32, and 128 hub tokens per latent frame. And they found that K equals 8 tokens is the optimal sweet spot.
Wait, really? Just 8?
Just 8. Using just 8 tokens per latent frame provides more than enough capacity to fully summarize the multi-agent interactions without choking the system. Going up to 128 tokens didn't meaningfully improve the FED scores at all. It honestly just wasted compute.
That is wild. Just 8 tokens acting as the dedicated server for the entire shared simulation?
Pretty much, yeah.
So the cross-agent information is essentially flowing through a 2-hop path. The agent tokens write their current state to the hub tokens, and then the hub tokens broadcast that aggregated world state back to all the individual agents.
Mathematically, that routing fundamentally shifts the scaling laws for multi-agent diffusion transformers.
Because you bypass the peer-to-peer mess.
Exactly. By communicating through the hub rather than pairwise across all agents, the per-block attention cost drops from big O of P squared down to big O of P.
Wow.
The compute cost now scales linearly with the number of agents.
Okay, so placing agents on a simplex stops the model from playing favorites, and the hub tokens keep the GPUs from melting.
Good summary.
We have an incredibly efficient, scalable architecture, but architecture alone doesn't guarantee a low latency, real-time streaming engine.
No, it definitely doesn't.
You can't just initialize these weights, throw data at it, and expect it to output 24 frames per second interactively. If you want a user to press WA to walk forward and see the frame update instantly based on their input, you need a heavily optimized inference pipeline.
Right, and the training distillation pipelines where we really get into the heavy ML engineering of this paper.
Yeah, let's get into it.
So the researchers built Gamma World on top of the Cosmos Predict 2.52 billion parameter model, and they designed this highly rigorous 3-stage training pipeline to essentially force the model to render quickly without hallucinating or losing the physics.
Walk us through stage 1, because they essentially start by building a model that is completely useless for real-time streaming, but, absolutely necessary for ground truth.
That's the bidirectional teacher. In this first stage, the model is trained with full temporal and full cross-agent visibility.
Okay.
It gets to look at the entire sequence of frames, past, present, and future, all at once, for all players.
Cheating, basically.
Basically cheating, yeah. This is incredibly computationally heavy, but it generates the absolute highest quality video. The purpose of this stage is to force the model to learn the deep underlying physics of how multiple agents interact in the world, without any blind spots. It maps out the absolute causality of the environment.
So what does this all mean? It's essentially a godlike model, right? It has perfect foresight, so it understands exactly how a block breaks or how lighting shifts when 2 players cross paths.
Exactly.
But obviously you can't deploy a godlike model to a user in a game because the user hasn't made their future inputs yet. You can't look into the future of a live stream.
Which necessitates stage 2, the causal student. Here, they utilize a technique called diffusion forcing paired with block causal attention. The student model is now forced to generate the video, block by block, and it is strictly constrained to attending only to past KV caches. It can no longer look into the future.
Got it.
It is learning to generate autoregressively, which is exactly what it will have to do in a production environment.
It's like taking off the temporal training wheels. The godlike teacher is showing it what the perfect physics look like, and the student is trying to replicate that quality while wearing a blindfold to the future.
Precisely. But there is still a latency issue.
Right.
The multi-step causal student from stage 2 requires way too many diffusion steps to hit that target of 24 frames per second. So we arrive at stage 3, conditional self-forcing distillation.
Oh, DMD.
Yes. They compress the generation process down into just 4 steps using distribution matching distillation, or DMD.
For those who might not be deep into diffusion distillation techniques, distribution matching distillation essentially trains a fast, few-step model to directly match the probability distribution of a slower, many-step model.
Yes. The 4-step student learns to match the high-quality distribution of the bidirectional teacher, but it achieves this auto-regressively, and it does it using the Sparse Hub Attention topology we discussed earlier.
And the brilliant part of this distillation pipeline is how it sets up the memory management for the streaming inference.
It really is.
Because they established that sparse hub attention, they can maintain entirely separate key value, or KV, caches for each individual agent's visual stream, plus one tiny shared KV cache just for the 8 hub tokens.
That separation is crucial. When player 2 takes an action and needs the next frame rendered, the system doesn't have to load the massive history of all players.
Right.
It just reads player 2's own past KV cache, and the tiny hub cache generates the next frame in 4 steps and writes the new state back to the cache.
It's a masterclass in aligning your attention topology with your hardware constraints. The sparse hub isn't just a clever trick to make the training loss go down. It translates perfectly into an inference topology that keeps memory bandwidth overhead incredibly low.
Yep. So we have the simplex geometry handling identity, the hub tokens handling the linear scaling, and a 3-stage DMD pipeline achieving 24 FPS.
So the natural next question for any practitioner is the empirical validation. How does this actually perform on raw metrics when evaluated on multi-agent Minecraft environments?
Well, they put Gamma World through an absolute gauntlet of tasks. Movement, mining blocks, combat, and building structures together.
Okay.
They evaluated it against standard frame concatenation baselines, which is the naive approach where you just mash the viewpoints together into one giant image and process it. And they also benchmarked it against Solaris.
And the results?
Across all metrics, Gamma World fundamentally alters the baseline. When you look at the freshet video distance, which is essentially the gold standard metric in ML, for checking if a generated video actually looks like real flowing time with consistent physics.
Right, lower is better.
Lower is much better.
Yeah.
Solaris was sitting at a score of 333.8. Gamma World achieved an FED of 184.1.
Oh.
Yeah. To an ML engineer, cutting the FED nearly in half is not an incremental update. That is a completely different paradigm of temporal consistency. It also consistently outperformed the baselines on FID, LPIPS, and SIM, proving that the frame-level fidelity and perceptual quality were vastly superior.
I mean, the quality metrics are great, but for me, the most striking data in the paper, the graph that really sells the architecture, is the scaling efficiency curve.
Oh, absolutely.
They plotted the generation latency when you push the system to 8 players. With the standard dense attention used in previous models, the latency for a single generation block rockets up to 611 milliseconds.
Yeah, half a second per frame.
It's completely unplayable. But with Gamma World's sparse hub attention, the latency curve stays incredibly flat. At 8 players, it hits just 246 milliseconds.
And the compute savings are even more apparent when you look at the self-attention FLOPs.
Right.
You know, the actual math operations the hardware has to execute.
Yeah.
Dense attention requires 7.6 teraflops to process 8 players.
Right.
Gamma World requires just 981 gigaflops.
7.6 teraflops down to under 1 teraflop. That is nearly an order of magnitude difference in raw compute cost just by changing the network topology to a hub-and-spoke model.
It is staggering. And importantly, that massive reduction in compute does not come at the cost of capability.
Right.
The ultimate proof that this architecture captures the true multi-agent distribution is their zero-shot generalization experiment.
Yes, I love this part.
Because of the permutation-symmetric simplex rotary encoding, they took the model that was trained purely on 2-player data, and at inference time, they just asked it to generate coherent 4-player interactions.
And it worked flawlessly. The agents navigated the terrain, they avoided bumping into each other, and interacted with the environment without any additional fine-tuning.
Zero shot.
That is the true power of getting the underlying geometry right. When the math reflects the actual symmetries of the physical world, the neural network doesn't just memorize training patterns, it extrapolates physical laws.
To synthesize the core value of this research, Gamma World proves that multi-agent video generation does not have to be an unscalable toy. By replacing rigid slot IDs with parameter-free simplex geometry and replacing dense big O of p-squared attention with linear big O of p-hub tokens, the researchers have created a deployable, real-time engine.
Yeah, if you are building the next generation of interactive AI, this paper is absolutely mandatory reading.
But before we wrap up, if we connect this architecture to the bigger picture of AI world modeling, it raises an incredibly profound, technical, and almost philosophical question for you to ponder.
Oh, lay it on us.
We discussed those 8 hub tokens that sit in the middle of the sparse hub attention block. If those 8 tokens are successfully aggregating the entire shared reality of all the agents and flawlessly passing that information back and forth to keep everyone's viewpoint consistent,
Yeah.
Are those hub tokens actually learning an emergent compressed representation of the objective laws of physics of that environment?
Wow, that is a staggering implication.
Think about the mechanics of it. The hub tokens do not belong to any specific agent. They are entirely independent of any single viewpoint or camera angle.
They're neutral.
Completely neutral. Yeah. If you could somehow isolate and decode the latent space of just those 8 hub tokens, would it give us a pure, objective, third-person state of the world? It suggests that in the pragmatic pursuit of making video generation faster and cheaper, we might have accidentally stumbled upon an architectural method for isolating objective reality inside a neural network.
That is a wild thought to leave off on. If you want to dive deeper into the mathematics behind the simplex encoding or the DMD distillation pipeline, check out the links in the description. Thanks for tuning in to this deep dive on AI Paper Slop, and we will see you next time.